A numeral system is a writing system for expressing numbers, that is, a mathematical notation for representing numbers of a given set, using digits or other symbols in a consistent manner. It can be seen as the context that allows the symbols 11 to be interpreted as the binary symbol for 3, the decimal symbol for 11, or a symbol for other numbers in different bases. The number the numeral represents is called its value. Ideally, a numeral system will represent a useful set of numbers, give every number represented a unique representation, reflect the algebraic and arithmetic structure of the numbers. For example, the usual decimal representation of whole numbers gives every non-zero whole number a unique representation as a finite sequence of digits, beginning by a non-zero digit. However, when decimal representation is used for the rational or real numbers, such numbers in general have an infinite number of representations. For example, 2.31 can also be written as 2.310, 2.3100000, 2.309999999, etc., all of which have the same meaning except for some scientific and other contexts where greater precision is implied by a larger number of figures shown. Numeral systems are sometimes called number systems, but that name is ambiguous, as it could refer to different systems of numbers, such as the system of real numbers, the system of complex numbers, the system of p-adic numbers, etc. Such systems are, however, not the topic of this article. Main numeral systems. The most commonly used system of numerals is the Hindu-Arabic numeral system. Two Indian mathematicians are credited with developing it. Aryabhata of Kusumapura developed the place value notation in the 5th century, and a century later Brahmagupta introduced the symbol for zero. The numeral system and the zero concept, developed by the Hindus in India, slowly spread to other surrounding countries due to their commercial and military activities with India. The Arabs adopted and modified it. Even today, the Arabs call the numerals which they use Rakam al-Hind, or the Hindu numeral system. The Arabs translated Hindu texts on numerology and spread them to the Western world due to their trade links with them. The Western world modified them and called them the Arabic numerals, as they learned from them. Hence the current Western numeral system is the modified version of the Hindu numeral system developed in India. It also exhibits a great similarity to the Sanskrit Devanagari notation, which is still used in India. The simplest numeral system is the Unary numeral system, in which every natural number is represented by a corresponding number of symbols. If the symbol is chosen, for example, then the number 7 would be represented by tally marks represent one such system still in common use. The unary system is only useful for small numbers, although it plays an important role in theoretical computer science. Alias gamma coding, which is commonly used in data compression, expresses arbitrary sized numbers by using unary to indicate the length of a binary numeral. The unary notation can be abbreviated by introducing different symbols for certain new values. Very commonly, these values are powers of 10, so for instance, if stands for 1, minus for 10 and plus for 100, then the number 304 can be compactly represented as plus plus plus, and the number 123 as plus minus minus, without any need for zero. This is called sign value notation. The ancient Egyptian numeral system was of this type, and the Roman numeral system was a modification of this idea. More useful still are systems which employ special abbreviations for repetitions of symbols, for example, using the first 9 letters of the alphabet for these abbreviations, with A standing for 1 occurrence, B 2 occurrences, and so on. One could then write C plus D for the number 304. This system is used when writing Chinese numerals and other East Asian numerals based on Chinese. The number system of the English language is of this type, as are those of other spoken languages, regardless of what written systems they have adopted. However, many languages use mixtures of bases and other features. For instance, 79 in French is Soixante-dix-neuf, and in Welsh is Pedwar bymygathrigain plus, or Pedwar ugan naminun. More elegant is a positional system, also known as place value notation. Again working in base 10, 10 different digits 0, 9 are used, and the position of a digit is used to signify the power of 10 that the digit is to be multiplied with, as in 304 equals 3 times 100 plus 0 times 10 plus 4 times 1, or more precisely 3 times 102 plus 0 times 101 plus 4 times 100. Note that 0, which is not needed in the other systems, is of crucial importance here, in order to be able to skip a power. The Hindu-Arabic numeral system, which originated in India and is now used throughout the world, is a positional base 10 system. Arithmetic is much easier in positional systems than in the earlier additive ones. Furthermore, additive systems need a large number of different symbols for the different powers of 10. A positional system needs only 10 different symbols. Positional decimal system is presently universally used in human writing. The base 1000 is also used, by grouping the digits and considering a sequence of 3 decimal digits as a single digit. This is the meaning of the common notation 1,234,567 used for very large numbers. In computers, the main numeral systems are based on the positional system in base 2, with 2 binary digits, 0 and 1. Positional systems obtained by grouping binary digits by 3 or 4 are commonly used. For very large integers, bases 232 or 264 are used, as, for example, in GMP. The numerals used when writing numbers with digits or symbols can be divided into 2 types that might be called the arithmetic numerals: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the geometric numerals 1, 10, 100, 1000, 10,000, respectively. The sign value systems use only the geometric numerals, and the positional systems use only the arithmetic numerals. A sign value system does not need arithmetic numerals because they are made by repetition, and a positional system does not need geometric numerals because they are made by position. However, the spoken language uses both arithmetic and geometric numerals. In certain areas of computer science, a modified base K positional system is used, called bijective numeration, with digits 1, 2, K, and 0 being represented by an empty string. This establishes a bijection between the set of all such digit strings and the set of non-negative integers, avoiding the non-uniqueness caused by leading zeros. Bijective base K numeration is also called K-adic notation, not to be confused with p-adic numbers. Bijective base 1 is the same as unary. Positional systems in detail. In a positional base B numeral system, B basic symbols corresponding to the first B natural numbers including 0 are used. To generate the rest of the numerals, the position of the symbol in the figure is used. The symbol in the last position has its own value, and as it moves to the left its value is multiplied by b. For example, in the decimal system, the numeral 4327 means plus plus plus, noting that 100 equals 1. In general, if b is the base, one writes a number in the numeral system of base b by expressing it in the form a(n)bn plus and minus 1 bn minus 1 plus and minus 2 bn minus 2 plus a0 b0, and writing the enumerated digits an minus 1 and minus 2 a0 in descending order. The digits are natural numbers between 0 and b minus 1, inclusive. If a text discusses multiple bases, and if ambiguity exists, the base is added in subscript to the right of the number, like this. Number base. Unless specified by context, numbers without subscript are considered to be decimal. By using a dot to divide the digits into two groups, one can also write fractions in the positional system. For example, the base 2 numeral 10.11 denotes 1 times 21 plus 0 times 20 plus 1 times 2 minus 1 plus 1 times 2 minus 2 equals 2.75. In general, numbers in the base B system are of the form: the numbers bk and b minus k are the weights of the corresponding digits. The position k is the logarithm of the corresponding weight w, that is, the highest used position is close to the order of magnitude of the number. The number of tally marks required in the unary numeral system for describing the weight would have been w. In the positional system, the number of digits required to describe it is only, for k 0. For example, to describe the weight 1000, then 4 digits are needed because the number of digits required to describe the position is. Note that a number has a terminating or repeating expansion if and only if it is rational. This does not depend on the base. A number that terminates in one base may repeat in another. An irrational number stays aperiodic in all integral bases. Thus, for example, in base 2, pi equals 3.1415926, 10 can be written as the aperiodic 11.00100000111111. 2. Putting over scores, n, or dots, n, above the common digits is a convention used to represent repeating rational expansions. Thus, 14/11 equals 1.272727272727 equals 1.27 or 321.32178787877878 equals 321.321778. If b equals p is a prime number, one can define base p numerals whose expansion to the left never stops. These are called the p-adic numbers. Generalized variable length integers. More general is using a mixed radix notation like for, etc. This is used in Punycode, one aspect of which is the representation of a sequence of non-negative integers of arbitrary size in the form of a sequence without delimiters of digits, from a collection of 36 AZ and 0 to 9, representing 0 to 25 and 26 to 35 respectively. A digit lower than a threshold value marks that it is the most significant digit, hence the end of the number. The threshold value depends on the position in the number. For example, if the threshold value for the first digit is b, then a marks the end of the number. So in numbers of more than one digit the range is only b9, therefore the weight b1 is 35 instead of 36. Suppose the threshold values for the second and third digits are c. Then the third digit has a weight 34 times 35 equals 1190, and we have the following sequence. A bar, California, 9A, BB, CB, 9B, BCA, 99A, BCB, etc. Unlike a regular based numeral system, there are numbers like 9b where 9 and b each represents 35, yet the representation is unique because AK and AK are not allowed. The A would terminate the number. The flexibility in choosing threshold values allows optimization depending on the frequency of occurrence of numbers of various sizes. The case with all threshold values equal to 1 corresponds to bijective numeration, where the zeros correspond to separators of numbers with digits which are non-zero.